Critical numbers and the first derivative test. Let's recall the following definition. If there's an open interval I containing a number c in which either f of c is less than or equal to f of x for all x in I, or f of c is greater than or equal to f of x for all x in I, then we say that f of c is a local extreme value of f. A local extreme value may be a local minimum, and it may be a local maximum. Let's also recall the following theorem. If f of c is a local extreme value, and if f is differentiable at x equals c, then f prime of c equals 0. Now let's state this theorem slightly differently. If f is a local extreme value, then either f prime of c is equal to 0, or else f prime of c does not exist. This picture shows a local minimum occurring at a point where f is not differentiable. This picture shows a local maximum occurring at a point where f is not continuous and therefore not differentiable. So let's give the following definition. A number c in the domain of f is called a critical number of f if either f prime of c is equal to 0 or f prime of c does not exist. And with this definition, we can now restate the previous theorem as follows. If f of c is a local extreme value, then c is a critical number of f. In other words, the local extreme values of f occur among the critical numbers of f. But be careful, the converse of this theorem is false, as the following pictures indicate. Here's a picture where f prime of c equals 0, but f of c is neither a local maximum nor a local minimum. Here's a picture where f prime of c doesn't exist, and again, f of c is neither a local maximum nor a local minimum. And finally, another example where the function fails to be differentiable at c because it's discontinuous at c. Critical point classification. Given a critical number c of a function f, how can we tell whether f of c is a local extreme value? And if it is, how can we tell whether it's a local minimum or a local maximum? For this purpose, we have the first derivative test. Let c be an isolated critical number of f. This just means that there are no other critical points nearby. In other words, there's an open interval containing c which doesn't contain any other critical numbers of f. We'll present the first derivative test in the form of a table where we'll indicate different ways in which f prime of x can change sign at a critical point c, as well as an indication of what the graph of f might look like at the critical point, and the conclusion that we draw from the first derivative test. If f prime of x changes from negative to positive at c, then f of x is decreasing on the left of c and increasing on the right of c, and its graph might look something like one of these two pictures here. So we can conclude that f of c is a local minimum value. If f prime of c changes from positive to negative, then f is increasing on the left of c and decreasing on the right of c, and this allows us to conclude that f of c is a local maximum. Now, if f prime of x does not change sign at c, that is, if it's negative on the left and the right, or else positive on both the left and the right, then we can conclude that f of c is not a local extremum. That is, it's neither a local minimum nor a local maximum. Example. Let f of x equal 3x to the fifth minus 5x cubed. Find the critical numbers of f and classify the value of f at each one as a local minimum, local maximum, or neither. So let's take the derivative using the power rule. F prime of x equals 15x to the fourth minus 15x squared. This factors into 15x squared times x squared minus 1, which factors further into 15x squared times x plus 1 times x minus 1. Now f prime of x is defined for all x, and it equals 0 when x is equal to 0, negative 1, and plus 1. So those are the critical numbers. Now let's make a rough sketch of the sign of f prime on each side of all three critical numbers. Now let's note that the sign of f prime is completely determined by the product x plus 1 times x minus 1, since x squared is never negative. Now when x is less than minus 1, both of those factors are negative for a net positive value for f prime of x. Between minus 1 and 0, x plus 1 becomes positive, while x minus 1 is still negative, and so f prime of x is negative between minus 1 and 0. Now this means that f is increasing on the left of minus 1 and decreasing on the right of minus 1, and so we conclude that the value there, which is 2, must be a local maximum. Now if x is between 0 and 1, x plus 1 is still positive, and x minus 1 is still negative, and so f prime of x remains negative between 0 and 1. In other words, there's no sign change at 0, and that's all because the factor x is squared. So f is decreasing on the left of 0 and decreasing on the right of 0, and so the value f of 0, which is 0, is neither a local maximum nor a local minimum. Now if x is greater than 1, then x plus 1 and x minus 1 are both positive for a net positive value of f prime of x. So f of x is decreasing on the left of 1, increasing on the right of 1, and so its value there, which is negative 2, is a local minimum. So summing up, the value of f at minus 1, which is 2, is a local maximum. 0, which is the value of f at 0, is neither a local minimum nor a local maximum. The value of f at 1, which is minus 2, is a local minimum. Another example. Let f of x equal x plus 2 times sine x. Find the critical numbers of f in the interval 0 to 2 pi and classify the value of f at each one as a local minimum, a local maximum, or neither. So let's take the derivative. F prime of x will be 1 plus 2 times the derivative of sine x, which is cosine x. So we see that f prime of x is defined for all x and equal to 0 whenever cosine of x is equal to minus 1/2. Now let's think about where that happens in the interval 0 to pi by looking at the unit circle and noting that the 2 points corresponding to an x value of minus 1/2 are as shown here. These points correspond to the angles 2/3 pi and 4/3 pi, so our critical numbers between 0 and 2 pi are 2/3 pi and 4/3 pi. Now let's make a sketch showing the sign of f prime of x near our critical points. Between 0 and 2/3 pi, we might choose pi over 2 as a test point. The value of f prime at pi over 2 is 1 plus 2 times 0, or 1, and so we conclude that f prime of x must be positive between 0 and 2/3 pi. Notice we could have also used pi over 4 or even 0 as a test point there. We can use pi as a test point between 2/3 pi and 4/3 pi. F prime of pi is 1 plus 2 times cosine of pi, and cosine of pi is negative 1, so f prime of pi is 1 minus 2 equals negative 1. And so we conclude that f prime of x must be negative between 2/3 pi and 4/3 pi. So we can already see that f of x is increasing on the left of 2/3 pi and decreasing on the right of 2/3 pi, and so its value there is a local maximum. Now between 4/3 pi and 2 pi, we can use 3/2 pi as a test point. The value of f prime at 3/2 pi is 1 plus 2 times the cosine of 3/2 pi, but cosine of 3/2 pi is 0, and so the value of f prime there is 1, and so we conclude that f prime of x is positive between 4/3 pi and 2 pi. So this indicates that f is decreasing on the left of 4/3 pi and increasing on the right of it, and so f of 4/3 pi must be a local minimum value of f. The value of f at 2/3 pi is 2/3 pi plus 2 times the sine of 2/3 pi, and since the sine of 2/3 pi is root 3 over 2, we have 2/3 pi plus root 3, which we've just determined as a local maximum. The value at 4/3 pi is 4/3 pi plus 2 times the sine of 4/3 pi, and the sine of 4/3 pi is negative root 3 over 2, so we have 4/3 pi minus root 3, which we've just seen as a local minimum value. Example. Let f of x equal x to the 2/3 power times 15x squared minus 72x plus 120. Find the critical numbers of f and classify the value of f at each one as a local minimum, a local maximum, or neither. For the purpose of taking the derivative of f, let's expand the product and write f of x as 15x to the 8/3 power minus 72x to the 5/3 plus 120 times x to the 2/3. By the Powell rule, the derivative of the first term is 8/3 times 15, which is 40, times x to the 5/3 power. The derivative of the second term is 5/3 times 72, which is 120, times x to the 2/3 power. And the derivative of the third term is 2/3 times 120, which is 80, times x to the minus 1/3 power. Now let's think of x to the minus 1/3 as 1 over x to the 1/3 power, and write all three terms over a common denominator of the cube root of x. The numerator then is 40x squared minus 120x plus 80. Note that you could think of obtaining that by multiplying the previous expression by x to the 1/3 over x to the 1/3. Now we'll factor 40 from each term in the numerator, and then further factor the numerator into 40 times x minus 1 times x minus 2. Now we'll notice that f prime of x is 0 when x is 1 or 2, and it's undefined at x equals 0. So our critical numbers are 0, 1, and 2. Now let's make a sketch showing the sign of f prime near each of those critical numbers. If x is less than 0, then x minus 1 and x minus 2 are both negative, and the cube root of x in the denominator is also negative, so we have three negatives for a net negative. So f prime of x is negative when x is less than 0. When x is between 0 and 1, the factors in the numerator of f prime of x are still negative, while the cube root of x in the denominator has become positive. So f prime of x is positive when x is between 0 and 1. So we can already tell that f of x is decreasing to the left of 0 and increasing to the right of 0, and since that's a point where f prime of x doesn't exist, we conclude that the graph of f has a cusp at x equals 0. Now between 1 and 2, x minus 1 is now positive, while x minus 2 is still negative, and the cube root of x is positive, and so there f prime of x is negative, and so f of x is increasing on the left of 1 and decreasing on the right of 1, and so we conclude that f has a local maximum there. When x is greater than 2, x minus 1 and x minus 2 and the cube root of x are all positive, so f prime of x is positive, and so we can conclude that f has a local minimum at x equals 2. Now in summary, f of 0 equals 0 is a local minimum value. The value of f at 1 turns out to be 63, and that's a local maximum. And the value of f at 2 turns out to be 36 times 2 to the 2/3 power, or the cube root of 4, which is approximately 57.15, and that's a local minimum value. Example. Let f of x equal 1 minus x divided by x squared. Find the critical numbers of f and classify the value of f at each one as a local minimum, local maximum, or neither. So we'll take the derivative using the quotient rule. The denominator will be x squared squared, or x to the 4th. The first term in the numerator will be the derivative of the top, which is minus 1, times x squared. Then we subtract the numerator times the derivative of the denominator, which is 2x. Now we simplify the numerator, noting there's a common factor of x, and the other factor would be minus x minus 2 plus 2x, which gives us x times x minus 2, all divided by x to the 4th. Now we cancel an x, and finally obtain x minus 2 divided by x cubed. So we see that f prime of x is equal to 0 when x is 2, and that's the only critical number, even though f prime of 0 is undefined. That's because 0 is not in the domain of the original function. So let's have a look at the sign of f prime on each side of the critical number 2. Now, if x is less than 2, but greater than 0, x minus 2 is negative, while x cubed is positive, and so the sign of f prime of x is negative. And if x is greater than 2, then the numerator and denominator of f prime of x are both positive, and so f prime of x is positive when x is greater than 2. So we see that f of x is decreasing on the left of 2, increasing on the right of 2, and therefore f of 2 must be a local minimum. And so the value there, f of 2 equals minus 1/4, is a local minimum. And it's the only local extreme value that f has. One final example to illustrate non-isolated critical numbers. Let's let f of x equal minus x if x is less than 0 and 1 if x is greater than or equal to 0. Then the derivative of f is minus 1 if x is less than 0 and 0 if x is greater than 0. Notice that f prime is undefined at 0 because f is discontinuous there. So we conclude that the critical numbers of f consist of all x greater than or equal to 0. None of these are isolated because given any one of them, every open interval surrounding it must contain another one. Now let's have a look at the graph of this function to make sense of what's happening at these critical numbers. The graph makes it clear that f of 0, which is 0, is a local minimum, and for every x greater than 0, the value there, which is 1, is both a local minimum and a local maximum. In fact, anytime a function is locally constant, that constant value is both a local minimum and a local maximum.